So, welcome to Craig Stevens. He's a principal scientist at NIWA, which is like the Instituto Oceanográfico Español, but from New Zealand. He's on a tour in Europe for several conferences, and he generously offered to visit us and try to find synergies, research synergies for future collaborations. So he's native from South Australia, and after some time in Australia and Canada, moved to New Zealand in the 1990s. Currently principal PI on the New Zealand Antarctic Science Platform Ocean Mechanics Project, and he's also a member of the Scientific Steering Committee for the Southern Ocean Observing System. He has held in the past roles of the president of the New Zealand Association of Scientists and chairs of the, I'm not going to pronounce that well.
Keep going. They won't know.
Aotearoa Wave and Tidal Energy Association. His research is focused on the ocean's role in climate, with focus on mixing in extreme environments. He is very interested on finding collaborations with European partners to apply for Horizon projects, because there is a recent agreement between New Zealand and Europe so that they can participate as European within Horizon programs. And his research is largely interdisciplinary, from what I learned yesterday on the Southern Ocean, and with collaborations with biologists and geologists and other disciplines besides physics. So I give you the word.
Yeah, thanks very much. Kia ora koutou, ko Craig Stevens toko ingoa. That's a Maori greeting, just saying hi, and my name's Craig Stevens. So thanks very much to David Amblis and Mariana for sort of making this visit possible. I've been in Norway at an ice shelf processors meeting, and then we've got a Rossi symposium in Naples next week. And I don't know if any of you folks have ever flown to the other side of the world, especially post-COVID. It's a bit of a mission these days, and so it's really nice to be able to put together a bunch of things to do and to talk to some interesting people. Just a couple of contextual things. I'm pretty sure I learned to swim in Barcelona. My parents, they moved from Australia to the UK when I was a kid, and we toured around a little bit. And I'm pretty sure, not in the ocean, but in a hotel swimming pool. My mum will probably tell me my memory's faulty. And the other thing is, I've actually spoken in this theatre before. We had a SCAR workshop here maybe about 8 years ago on sort of Antarctic ecosystem processes. So I'm going to split today's talk into two parts. Very much sort of pictures and sort of broad descriptions. So if you want more details, if you want some of the sort of science behind it or some of the references, either ask a question or come and chat afterwards, and we can sort of dive in a little bit deeper. But I'll split it into two parts. Oh yeah, and the other point is, thanks for allowing me to speak in English, because you didn't want my Spanish. I can assure you. So two parts. The first part is just around some of the sort of processes and sort of scientific themes that we work on in the oceans around New Zealand. And then I'm going to talk about sort of one of my main areas of work for the past decade on Antarctic oceans. And so the first point to note is you can take a view of the planet that has New Zealand, or Aotearoa. It's the Maori name for New Zealand. And there's a lot of ocean, and there's not a lot of taxpayers. And so we're having to do a sort of a lot of science. We've got sort of jurisdiction, if you like, or presence for a lot of the ocean without necessarily a lot of resources to go behind it. The other neat thing about the system is that Aotearoa is essentially a submerged continent. And so you sort of think of continental shelves as being sort of a narrow ribbon around the continent, but if you peel away the upper couple of 100 meters of New Zealand, you reveal a much wider landscape. And of course, This has been dramatically evolving over the last few million years. And part of that landscape and that submerged landscape is it's kind of sitting as a divider in the oceans. So I promised I wouldn't walk around, so I'm actually having to hold onto the table to not walk away from the microphone. But is that going to work? Sort of. To the north, we have currents that come down the east coast of Australia, the East Australian current, so a boundary current that then separates away from Australia and comes around the top of New Zealand. So this is all sort of warm water from the tropics. At the other extreme of this sort of the 2,500 kilometre long landmass, we actually have the Antarctic circumpolar current. And so those two currents kind of merge and make for a very sort of divided east coast to our ocean environment. So what's happening on the east of the North Island is very different oceanographically to what's happening on the east coast of the South Island. But then the Tasman Sea to the west is sort of caught between, it's kind of a shadow zone, if you like, and so it's just a pile of sort of slowly moving eddies, and so not particularly sort of dynamic. However, the sort of upper ocean heat content, and I'll get onto that a little bit later, is very important for our weather, because as you can imagine, most of our weather comes from the west, and the amount of moisture and the temperature that picks up then dominates our sort of environment on land. So I guess we have these sort of three systems: the warmer subtropical waters from the north, the subantarctic waters from the south, and then this kind of eddy zone in the Tasman Sea. And so with that small population, that very large amount of ocean, and the modest level of taxpayer funding, there's not a lot of oceanographers per unit area of ocean. And so there are probably more oceanographers in this room than there are in New Zealand. And also with that, there's also not necessarily a lot of data. And so the image on the left are the number of CTD profiles in a particular box through all history, if you like. And so there are really just a couple of hotspots where we've had particular experiments, and then lots of the rest of the domain is characterized by perhaps one or two sets of observations. So it's, that's as we'd say in English, that's a blessing and a curse. It's difficult because we don't necessarily have a lot of data, but from a scientific perspective, you don't have to go very far to be making some new discoveries. So it's exciting in that regard. Of course, I'm sort of a little bit hiding the light under a rock, if you like, because whilst those vessel-based CTDs are quite limited, of course the Argo program over the past 2 decades has dramatically changed how we measure and connect with properties of the ocean. And of course you'd be familiar with all this sort of, so these are Argo surfacing, and gives you a little tail indicating the trajectory of the Argo float. And of course what you note is that the continental shelf around New Zealand is, because Argo floats generally operate in 2,000 metre depths, we're not necessarily getting data on those continental shelves in our sort of plateaus around Zealandia. So we still have a problem, even though the Argo data network is changing how we look at the ocean processes. 2 points. One of our ships is responsible. It's the ship that has delivered the most Argo floats of any ship in the world, which is kind of a nice record. In the early 2000s, it was recognized that the Southern Ocean was quite a data gap in terms of Argo deployments. And so the Argo program set up a sort of a dedicated initiative to get more floats into the Southern Ocean. So our small sort of 20-metre vessel, the Kaharoa, has dropped off the most of these. And I guess the other thing that we're starting to do is put more of these floats onto continental shelves. So the original Argo design, many of you be familiar with, you only put these into deep water, but we're now more able to park them on one of these plateaus. And so you can see some of these floats were deliberately put in shallower water than normal, and they're able to sample there for 3 to 5 years. So that's, the Argo program is evolving. And I guess the other contextual thing for doing science, in fact, living in New Zealand, is that it's essentially the last major landmass on the planet to have people turn up. So Europeans arrived in the sort of the late 1700s, early 1820s, 30s, and Maori before that arrived in around 1100. And so really there's only kind of a 1,000-year history of occupation by humans, but also when the Europeans turned up, unlike in most other settings, there's actually a deal was signed. So there was actually a contract signed about how Europeans would interact with the original inhabitants. And so much older systems like Europe have got many more layers, and those kind of deals get buried over thousands of years. This deal is still operating. And so part of that is sort of access to resources, but also access to knowledge. So when we write a proposal, and I'm pretty sure this is unique, you're starting to see aspects of this in Canada and Australia, but up front in the proposal for the research, we're actually having to explain how it relates to sort of Maori culture and economies, and also how Maori scientists will be involved. And so it's quite a unique and challenging aspect of what we do. From an ocean perspective, it's pretty legitimate kind of work to be thinking about, because Pacific Navigators were some of the earliest navigators that were actually able to deliberately cross, a very large ocean system with some control and with some knowledge. And so, the original sort of European view, maybe 50 or so years ago, was very much that Maori migration was basically people being blown off course in canoes. But we're becoming much more aware of the deliberate sort of skills in navigating the environment with the technology that was around 1,000 years ago. So very sort of in-depth heuristic knowledge of waves, star patterns, and wind fields and stuff like that. So it's from an oceanographic perspective, it's pretty satisfying and legitimate work to sort of connect our views on science with how these navigators were operating 1,000 years ago. Okay, I'm just going to shoot through a few sort of slides that are giving examples of where ocean processes are researched in New Zealand, I guess. And one of the nice ones, which is a sort of a merging of physics and biology, is rock lobster, one of our largest export fisheries. And so they start out as very small larvae. And so not necessarily sure of their actual origin, but some of these larvae come from as far away as Australia, which is 1,000 or several thousand kilometres off that way, and they come across in those ocean currents that I showed in an earlier slide. What they then do is at this sort of life stage, they sit in all the sort of eddy structures that are sitting opposite on the east coast of the North Island. At some point, they make a decision and swim to shore. Swim, we don't really understand how they make the decision and how they actually manage to navigate across these eddies. This is around about 800 kilometres in scale, but they migrate and will come into shore. And so you can imagine with a changing climate, there's potential for this western boundary current to change, and these eddy structures will change. We may be seeing this very important fishery and also a key part of the marine ecosystem. It may undergo changes. Not a marine species, but highly relevant to coastal oceanography in New Zealand. So historically, you may have a view that before Lord of the Rings, what New Zealand was known for was sheep. and production of wool and lamb, mainly for the UK market. But the last sort of 20 or 30 years has seen a real shift to dairy production, to the extent that our sort of environmental rules around impacts on the land aren't necessarily catching up. And so, you literally have some of these dairy farms have sort of the waste production that's equivalent to a small city. And they're, of course, not regulated in anything like the regulations that you have when you put in a city somewhere. And so this ends up in the soil, but then it ends up in the streams and it ends up in the rivers. And so for us, there's strong interest in the fate of fresh water that's flowing out of rivers, and the sediment and the pollutants that's bound up in that, where that settles and where that accumulates. And coupled with that, I'm trying to remember what my next slide will be, with the changing climate, we're getting more tropical cyclones. And so we're getting more, let's say, I've got to be careful with the determinate words. We're not necessarily getting more tropical cyclones, but they're getting stronger, so the impacts are growing. And so the other aspect of New Zealand is it's very small but steep. And so we have really quite short timescales for when a storm arrives, when that material gets flushed down a river and then plumes out into the coastal ocean. And so we spend a lot of time modelling transients in the coastal ocean, both in terms of fate of fresh water, but also the sort of sediment particles that are trapped. And this is why I was trying to second guess my next slide. The other aspect around the Southwest Pacific is that we're tracking our surface temperatures of the ocean are around 3 times that of the global rate of increase. And so, and so that's the surface, that's the SST, so that's from satellite, so of course that's really only the upper centimetre or so, and you need a much more in-depth understanding of what's happening beneath the surface. But we know enough from Argo to know that this sort of effect is happening through the upper ocean. And so we're seeing dramatic increases around the southeast corner of Australia, and then a little bit off to the east of the northern part of New Zealand. So we're feeling the effects on our coastal ecosystems from this warming faster than anywhere else in the world, essentially. Right, so this is where it's out of order. Lots of floods from tropical cyclones. In terms of oceanography, and especially continental shelf oceanography, we have a reasonable amount of work, at least in the past, on the impacts of aquaculture, both in terms of, so this is a cage with, say, 40,000 fish that's the size of this room, and they get actively fed, and you have aquaculture industries in Spain. So these are a point source of pollution, and so you obviously want to understand where that's spreading, but also at the same time, with that changing climate and that increase in temperature and changes to the oxygen dynamics, the actual viability of these industries is changing. And you know, from a New Zealand perspective, it's long in the north-south direction, so you just have to keep moving your industry further south, but at some point, both for ecosystems and for industries, you run out of land, or you run out of coast, and you're no longer viable. Just some other snippets of science that we're starting to think about. Historically, New Zealand's been a little bit like Norway in terms of renewable, and Iceland in terms of renewable energy. For decades, it's actually had very good renewable energy profiles. We've generated a lot of electricity from hydroelectricity, to the extent that I think we've actually a little bit now behind as there's a push to moving towards both 100% electricity from renewables, but also reducing those non-electric uses of energy and shifting them to electricity. So we're starting to think about offshore wind energy. And so we have none of this technology at the moment. We have many onshore wind farms, but we're just starting to think about how we will go. We're sort of looking to develop some of the first farms in this southwest corner of the North Island. And so there's lots of things we're going to have to work around with that, both in terms of working with Maori, working with fisheries, and understanding the impacts of this kind of work, because a lot of the sort of environmental impact for this kind of work relates to seabirds and marine mammals. And so experiences in Europe and North America won't necessarily be transferable, because the species structuring will be different. This other perspective on renewable energies from the ocean has actually been explored for quite a bit longer, but also with the same outcome, that we don't actually have anything in the water at the moment. But we have quite small tides in New Zealand. However, this is the M2 tide, so the semi-donal tide rotating around the two islands. Red is around plus 2 meters, blue is around minus 2 meters, so it's only really a 4 meter tidal range. And so there are some parts of, say, northern France or northwest Australia where you're like 4 times that, 3 times that. What we do have, though, is that there's a hole in the middle of the country, and it's high on one side and low on the other side to an extent. So you're actually sort of doubling your tidal height, if you like. And so through this 25 kilometer wide gap, you can get sort of 3 or so meter per second flows. And it's one of the neat things about visiting Spain is some of the topic that I work on is turbulent mixing in the ocean, and the Straits of Gibraltar is where some of the early work in the 1980s was conducted to understand how these sort of tidally driven systems can generate really high levels of turbulence. Gibraltar is very much a density driven system. Our system is very barotropic, it's very tidal, and so everything's kind of moving in one direction at the same time. But along with the sort of the energy extraction potential through this gap between these two islands, it's also potentially a barrier to ecological or biological connectivity. And so we work on exchange between the two islands. Because the flow is so great, you tend to see things will get pushed through the strait rather than crossing the strait, if you know what I mean. See if I can actually get that to play. Yeah. So the previous slide was modelling work, but we also do some in situ observations with drifters. And it's kind of remarkable that you can drop some drifters about 30 kilometres apart, and they actually end up in different oceans within about a month. One of the other, and so this was actually what brought me to Spain, is discussions with the University of Barcelona around canyon processes. And so these are sort of breaks in the continental shelf edge where you've got preferential pathways for drainage, but also nutrient pathways being pushed up onto the continental shelf. So the light blue is maybe around 150 meters, and we're down to around 3 kilometers. And so my office is about there, and so it's about 12 kilometers, and we can be sampling a reasonable sized ocean canyon. What's a little bit unique about this system, so most ocean canyons will be something like this, where they run up to the edge of the sea, and so there's a barrier there. What this particular set of canyons runs up against is Cook Strait, where you've got this really strong tidal mixing pushing in and out. And so there aren't so many canyon systems like this around the world. And so this is actually an area we've already had discussions about collaboration with people here, and where there's a canyon meeting in Wellington in December. There's some folks from here will be attending. Slightly grainy photo, but we also have earthquakes. And so this is from a road that's actually just down there from a 2016 Kaikoura earthquake. And so large slips on land, blocked roads, damaged buildings, etc. But also the same sort of deal was happening in some of these canyon systems. And so it's a natural experiment, if you like, to look at the recovery times of the ecosystems that live and evolve in these canyons. And I think the take-home message, and I don't know if my canyon colleagues would support this, but the actual recovery in lots of places is perhaps faster than they expected. Okay, sort of going to switch gears a little bit and talk about Antarctic research. And so two aspects of this. So New Zealand is kind of just down off the screen here. We actually have some legal jurisdiction over a part of Antarctica. It's called the Ross Sea Dependency. And so not all nations necessarily support that agreement, but we do have sort of logistical and sort of search and rescue type ownership over this area. And the other point is that, so I've had 15 expeditions to Antarctica and I've never sailed there once. So we fly to McMurdo Station, and so I guess several times I've actually left Antarctica in the morning and been home in my own bed that night to sleep. Whereas some of my colleagues that will sail to do field work in Antarctica will spend 10 days on a boat getting seasick. I may well have that experience this coming February though. So I'm going to talk about some recent work on the southernmost part of the ocean on the planet. And so Antarctica's here, New Zealand is sitting down here, South Pole is here, and this is the Ross Ice Shelf. And so it's the largest ice shelf on the planet. It's around the size of Spain in terms of area, and it gets to around 82 or 83 degrees south. And so I'm going to talk about some experiments in estuaries along the coast. And so why you would go and sample an estuary under ice is because looking at model projections of sea level rise for the coming century, there's a reasonably sort of tight band depending on the framework of the model you're using, the conditions that you're using, but there's a whole family of simulations and projections where they've added in uncertainty around the sort of the survival of all of this ice sheet with a warming ocean. And so they're very unconstrained by observations. And so the type of observations that I'm going to talk about, there have been around 4 ever conducted, right? So there are many processes yet to be understood. And it's part of a program where I've been working with colleagues, and we've tried to build up a transect from the continental shelf break right down to this furthest south part of the oceans, trying to understand the sort of the ocean trajectory this way to bring warm water under this ice to melt, but then the results of that melting, how that works its way off north. And so this is our general challenge. We're working on an ice sheet that's around 800 kilometers in extent, but only really about 800 meters in the vertical. So if you actually were to put this in 1-to-1 scale, it would be about a centimeter high and would stretch across this room. So it's this tiny little crevice, this narrow cave of warming ocean. But if this red stuff, if this warming ocean significantly warms and starts significantly increasing the rate at which this ice melts, then sea level rise will do what we saw in that earlier slide, and coastal cities around the world will be moving. So we started this work over a decade ago with a borehole through this, and we've been slowly looking at other systems over the last decade. But where I'll focus on today is our most recent experiment to the beach, to an estuary, and so we're actually upstream of the coast. So if you imagine you're on the coast and there's an estuarine inlet, we're actually away from the ice shelf cavity and we're sort of on land, but we're looking at the hole in the ice that's been melted by a channel of meltwater that's coming off the continent. And so it's about 5 kilometers long, and it's under about 400 meters of ice. And so if you go to these systems, it looks like this. It's essentially the flattest view you can have on the planet. You can rotate 360, there's nothing on the horizon, the ice surface barely varies. But if you go down several hundred meters, you've got this warming ocean. And the key element to making our work possible is technology called hot water drilling. And so basically, you set up a reservoir of water at the surface that's maybe plus 5 degrees Celsius, and you have a technique for hosing it into the ice and actually boring your way through the ice with a pool of hot water. And so it takes about 2 weeks to set this gear up, and then they melt through in about 12 hours, and then we go to work. And so lowering a camera down a borehole, so this is a part of the ocean that's never been sampled before. The diameter of the hole is around 35 centimeters. You can start to see ice crystals forming. You actually have a race against time once you melt these holes, because the ice itself is minus 10 or something like that. Everything is desperate to refreeze, and that's our greatest challenge, is equipment getting frozen in, and there's a growing list of equipment that's still there. This view is just about to leave the ice underside, and we're looking up, and so we've just popped out, and that's the base of the ice shelf there. That little lip actually is a product of the melting process, and it's quite a dangerous aspect of what we do. It's very easy to wedge your equipment against that. But we've now got our sensors in a part of the ocean that's never been measured before. And so the first thing is we did a scan with an altimeter to look at the shape of the cavity that we were in, and we sort of thought it would be this nice broad sort of open system that might be really quite wide, and it was totally wrong. I guess that's the other thing, is we've done about 4 or 5 of these, and every time it's not what we thought it would be. And so it's a strong motivation for going somewhere and measuring something for the first time. Well, what we found was that it's a narrow slot around 200 meters high, and so this is a cross section. And you know, most of our oceanic cross sections we squeeze in the horizontal, right? So to make it fit on a page. This is 1-to-1, and so it's actually this vertical slot, pretty unusual for an oceanic system. And I worked out a scale bar. So this is your very, very nice cathedral that's just up the road, and it's essentially the same height as the cathedral, but it's around having 50 of these strung end to end. But I found it quite instructive to just stand outside the cathedral and imagine it's all dark, and just imagine our little light being lowered down from the surface into this cavity that had not been sampled before. It was quite neat. But the CTD structure, the conductivity, temperature, and turbidity structure is also pretty neat. What we found is that there's around 2/3 of the water column is the ocean sitting at the bottom, and it's found its way in. But then this layer here, and we know this because there's a bulge in turbidity, so the orange is turbidity. This is water that's snuck out from underneath the ice sheet. So this is the water that's sort of lubricating the ice that's then flowing into the ocean and causing sea level rise. And so there are almost no observations of this kind of system happening. We're able to estimate that our flow rate in this subglacial discharge is really small. It's less than a cubic meter per second. However, there's plenty of evidence in the related sediments and the ice in the region that we think that this is sort of like a background flow, and every now and then there's a massive flood comes through. And so one of the things we're hoping the instruments that we've left there will capture one of these flood systems. But as we first get a camera beneath the ice and have it slowly spinning around. These lumps and bumps are around 1 meter in scale. And so the equations that you use to model to tell you how much ice is melting as a function of flow and temperature and salinity assume this is flat. So we have to rethink that. And also the other thing is you see lots of particles sinking out in this system, but we're almost certain that this ice is actually very clean ice. And so these particles have actually got nothing to do with the ice. They're caught up in the boundary layers, the meltwater boundary layers that are flowing up the sides of our cathedral and bringing sediment from near the bed, dragging it up and then dropping it. I think this may be the only data plot in the whole talk. What normally happens with these sorts of experiments is because of all that freezing, people typically only go in and do one sort of snapshot of what's happening. We've developed a technique that uses a lot of gasoline to keep that hole open for maybe 2 weeks, and it gives us time to do a lot of measurements that don't normally get done. And so we're able to drop a high resolution thermistor through this water column repeatedly over 24 hours, and our nice layer of subglacial discharge is being pumped by the tides. So the tidal elevation is around 1 meter. This is going up and down by about 20 meters. It's also semi-diurnal. It's also at around a sort of 12-hour period. The actual tides in this region are 24-hour tides. They're diurnal. And so there's some kind of harmonic process going on either within our cathedral or actually within the cavity close by. So our system, our estuary, is around 5 kilometers long. We've worked out that we've got water with oceanic properties sneaking in at the bottom. So if the oceans in this part of Antarctica start to warm, then this kind of system will start to change. Then we're able to detect the outflow, what's flowing out from beneath the ice sheet, and we see that as being quite a low flow rate at the moment, but maybe there are big flood events. And also I showed you the stuff draining out right near the surface. We actually think that that's a little bit of a local effect, and so there's actually a kind of an inverted basin right at the top there, and so that's not so connected to this subglacial discharge. The other thing, again, you've got to go somewhere and have a look, right? We've done a number of these experiments before, and if you see a single animal in like a 2-week experiment, you used to write it down in your logbook and you run around the camp and tell people. So the first time we put the camera down, A, we didn't have the focus sorted out, so apologies, but B, there was a swarm of amphipods. So the dots are 10 centimeters a second. This is sitting at the seafloor. We're about 1 meter above the seafloor in this cavity, and these amphipods swarmed around the camera. And so we'd never seen this before. We're 400 kilometers from the open ocean. And so this is presumably some local population that manages to work without having light. And so we thought, oh, okay, we messed up the focus. That's okay. We'll fix the focus and get another shot. Every time we put the camera down, there were fewer and fewer amphipods there. So either there's frontal structure related to the tides that we're talking about perhaps, where this species preferentially hangs out, and so there are sort of focused areas of population, or by lowering something that's 10 bazillion times brighter than anything they've ever had to deal with, we've made this population go somewhere else, is the best case scenario, really. The other thing we do is we leave instruments behind, and so it's a technique where we can adjust the equipment that we put on the line, lower it down, and it all freezes in, and some of this gear will last as long as 4 years, and it'll telemeter data back. And so you can be downloading what the water column is doing at your office, presumably somewhere warmer. One of the interesting things from this last experiment was 4 days after we deployed that mooring, we had the Tongan volcanic eruption. So 2021, I think the largest volcanic eruption in the last century. The eruption happened here. There was an atmospheric pressure wave. So this is pressure in our cathedral gap, right? This is from one of those sensors that we deployed. And because the ice is attached to the land as opposed to out in the shelf where it's actually floating, it's actually able to respond to pressure changes in the water. And so we actually see the atmospheric pressure wave come through, and then around 13 hours later, we see the signature of the tsunami. So the tsunami has left Tonga, worked its way all around the Pacific Basin, come up onto the Ross Sea continental shelf, hit the front of the Ross ice shelf itself, where the water column halves, and then made its way to our cavity. And the interesting thing is, this corner of the Ross ice shelf continued to bounce around for maybe 4 days. And so we're still sort of analysing, there's never been this kind of data set collected in the past, and so we're analysing what happens with a tsunami when it hits that, the front of an ice shelf. So this is not the front of the Ross ice shelf, this is the front of the Nansen, which is a little bit up the coast, but there's nowhere on the planet where there's anything geophysically equivalent to this, right? This is around 30 meters high, and there's another 80 or so meters beneath it. It's somewhere where the water column, in the space of a few meters in the horizontal, the water column halves or is reduced by a third or something. So no computer model handles this. And so climate models actually put a wall there. So there's nothing underneath, it's a solid wall. And if you think when the helicopter pilot did that, I didn't freak out, you were wrong. This was, both for me, the most amazing and the scariest flight I've ever taken. But also this sort of sharp transition, it's an active area of research as to how water gets underneath and gets back out again. And in our part of Antarctica, the ocean is very cold underneath these cavities. So in some parts of Antarctica, the ocean is relatively warm, but where we are, the ocean is so cold it's actually colder than the freezing temperature. And so something that we're actively working on is that you have ice crystals will form within the ocean and then slowly float up and build that ice from underneath out of ice crystals. And we had a great session yesterday with folks here around sea ice and salinity detection from satellite. And so, this understanding, this kind of contribution to a sea ice thickness is again another aspect where we're at the forefront of science that's entirely relevant to climate. So a few sort of take-home messages for the ice shelf work. Tides are always important, and this is a real challenge, because if you're trying to model climate systems for the next century, being told by an observationalist that something is happening over 12 hours is really important. That's a challenge. We've discovered subglacial discharge, but they're very small rates of flow, and so we're trying to understand the variability and just promoting the view that all around Antarctica, underneath these ice shelves, you actually have estuaries. And just to finish off, Mariana made the point at the start, one of the motivations here, so I don't know if you know, but Australia is allowed into Eurovision, but New Zealand is allowed into Horizons EU. So we're trying to work out what that actually means in terms of collaboration, but like the talk yesterday, where there's a group here that are entirely focused on very relevant topics, relevant to New Zealand and global science. I think there are some real opportunities here. And I'll just finish with a bit of tourism. I've had a little bit of tourism around your city. This is our most recent camp, and we've just dragged the camera through the living area. This is all on 400 meters of ice and then ocean beneath. And so all the action happens in this very large orange tent. One of the nice things about our work is we tend to work in summer, so it's only sort of -5, -10. So that's quite nice. We have a sort of an area out the back of the tent where we lay out all the cables, and so that's quite an area you have to be careful. So preparation areas for instruments that get lowered down the hole, and then through to some of the science areas. This is where we keep all the grad students as they analyse the data. Most of these tents are heated, so it's actually quite comfortable. We even have a shower and a little laundry out there. Quite often our experiments, we won't all be New Zealanders. This particular experiment had about a third of us were from the US. We often have Korean and Italian and Chinese collaborators. The living area, we typically have Christmas out there. So it's kind of nice to have a bit of a home base. And this is where we keep all the food, which is, you know, the most important bit. So I'll leave it there. Thanks for listening, and any questions? Kia ora. Thanks.
I have a question. Very general. So you mentioned that climate models do not resolve these underneath the ice sheets estuaries, let's call it. Mm-hmm. So how it could affect the way we simulate the ocean circulation, larger scale, for instance, like resolving these circulation pathways could affect, I believe, the time decay of ice sheets, or could affect the deep water mass formation.
Yeah.
This type.
I mean, the modelling community recognises that it's a problem. They just can't sort of get the scales to I mean, the next generation of climate models are starting to think about having these cavities. So what they do is they estimate a rate at which these regions must be melting and putting fresh water in, and they call them hosing experiments, so like a hose, a garden hose. And so they actually pump fresh water along the boundary. And so that's fine, but you know, the big question is what depth do they inject it? You know, because fresh water is one thing, but you know, salinity is such a controller of what depth it flows out at. It's an active area of research as to whether you put it at the surface, mid-depth, or over the full water column, and how much you actually pump out. So that's okay. You can use that to help understand the global ocean circulation, but it doesn't help you get the melt rates right for the ice sheets, which you actually need that number to work out how much fresh water you pump out. And the other big challenge is all of this is very intimately entwined with sea ice growth and production. It's a 3-hour version of this talk where you look at, you melt underneath an ice sheet, that increases the stratification in the ocean, that makes it easier to form sea ice. You form more sea ice, that pumps more salty water underneath the ice shelf. And so there's a sort of a lot of loops going on, and presently models are, you know, climate models are struggling with sea ice areas, you know, as well. So multiple challenges, but that's why we're here.
Thank you for the talk. I had two questions, but maybe sounds very stupid, but when you are talking about the boundary model and this sea ice cliff, or this ice cliff, I was wondering if it has a variation in the position during summer, during winter, and if it was considered in the model. And the second question was related to the change of temperature per decade that you have shown. They were like a freshening, or it was colder in the south side of the map, and I was wondering for why. What was the reason for that?
Okay, the first part relating to this sort of system, yeah. So this is ice sheets, ice shelves all around Antarctica are always moving towards the ocean, away from the land, and at some point they'll break off and form icebergs, and so whether or not that breakup is increasing and we're getting more icebergs, or whether there's more melting, is again something that's been actively researched. I guess the challenge is that these changes here, some of them can happen very rapidly, but some of them take decades, and we've only really been able to observe things for a couple of decades. But at the moment, the loss of ice, freshwater ice from Antarctica, is around 50-50 in terms of melting versus icebergs forming. And so especially in fact, this piece of ice, about 2 years after this was filmed, this broke away, and it was 20 kilometers by 5 kilometers, and then it moved out into the Antarctic circumpolar current. So yeah, I don't know if that quite answers your question, but it is a changing system. It doesn't change very rapidly until the calving happens. Your other question around why it was warm at the north and cold at the south, relating to New Zealand, that's that whole point that we're actually, the source waters come from very different parts of the global system. So to the north of New Zealand has all come down past Queensland and Indonesia, and so it's that warming is happening there. The water to the south is from the ACC, the Antarctic Circumpolar Current, and so that is not warming nearly as much. And it's a colder system, and it's mixed more vigorously in the vertical. So we're very much an ocean of two halves, which again, it drives a very dynamic sort of climate in New Zealand. We've got hot and cold really quite close to one another, and so it's quite windy where we are. We've got these gradients in thermal driving. Okay.
Back to New Zealand, I was wondering how you could explain actually how much like the regional carbonation local oceanography.
Yeah. Not my area. And I guess what I find interesting is that it's different every time. So we think about El Nino and La Nina as being two different states, but there seems to be strong subtleties within them. But from a land perspective, and this gets back to my point around our weather coming from the Tasman, because we have this big mountain range up the middle of the country, we can actually have increased winds driving much more rainfall, but it'll actually get trapped by the mountain ranges, and so it'll be very wet on one side, and we'll actually have droughts a few sort of tens of kilometers further east. So yeah, but with this growing El Nino, we're waiting to see what happens. It sort of seems to be different every time.
Well, very interesting, and thanks for the talk and coming here.
Yeah. Most welcome. Kia ora.